Hello, everybody, and welcome back to our math class. Today, we are going to solve an ARML question from 1992, a geometry problem that will actually get us to think a little bit more as to how we can use the angle bisector theorem. But let's see what the problem is saying. So we've got a triangle ABC, and then we've got 2 points D and E on AB and AC. Well, there you go. Here's point D, here's point E. And we've got this angle bisector AT now. Well, this is point T on BC. So these two angles are equal to each other, as you can see on this diagram here. All right. So, and this angle bisector intersects DE at point F right here, no? And then we've got some dimensions given to us. AD is 1, BD is 3, AE is 2, and EC is 4. As you can see here, AD is 1, BD is 3, AE is 2, and EC is 4, right? All right. And then what we are asked to compute is the ratio AF over AT. So I strongly suggest that maybe you guys take a minute, pause the recording of this class and see if you can solve this problem on your own, because actually this is a very interesting question to me in the sense that it's not entirely obvious what to do here, but the problem can be solved with absolute basic knowledge, which is the beauty of geometry, where quite often, you draw a line, you draw the proper line, you may construct various objects that will enable you to make progress through your problem. So here's my solution to this problem. Well, what are they trying to compute here? Well, this is AF over AT, no? Well, there's nothing obvious that would relate these two lengths. As you can see, even on the diagram, right? DE, well, it's not parallel to BC. And the problem is not that they don't look parallel. They are not parallel, no? Because if they were to be parallel, AD over AB would have to be equal to AE over AC. And it's easy for you to see that that's not happening. So how do we figure out this ratio? Well, maybe you can say, well, okay, maybe one way of attempting a solution would be to actually express AF. Now, AF and similarly express AT. Well, this is doable. There are formulas that give us the length of angle bisectors, and in themselves, those are interesting computations for you to think about or learn about. But they are fairly complicated, and I was thinking, how about I don't go there? How about we try to solve the problem with sort of minimum theoretical knowledge? I don't even know if those formulas are crazy useful in this particular setup. But okay, so let's say I don't want to compute AF and AT or express them because we don't know DE, we don't know BC, so we can come up with some formulas, but let's postpone it at least for now. And still, how do we actually figure out AF over AT? Because like I was saying, we have no similar triangles. It's not obvious as to what we have to do. Well, here's one idea that I was thinking of. Well, how about we construct heights from F and T onto AB? So let's say these two angles are 90 degrees here. Okay, let's say, just to keep it simple, let's say this is X and this is Y. So now we actually do have similar triangles, right? Namely, this little triangle here and the bigger triangle here. And then writing the similarity ratio, right? AF over AT. So AF over AT, that's equal to X over Y, no? Okay. Well, so now we actually want to compute the ratio x over y. How do we do it? Well, so now, for example, what you can do is this. Let's say, how do we go from x to y? Well, how about we go from this height, which is x right here, to the height from E onto AD. Okay, let me call this Z for now. Again, I'm constructing here this perpendicular. Well, again, now we have other similar triangles, namely this triangle right here and this bigger triangle right here, no? So again, writing the similarity ratio, x over z is going to be equal to df over de, no? So df over de. Well, do we actually know df over de? Well, actually, now we can use the fact that AF, so AF here is angle bisector in triangle ADF. So if we use the bisector theorem, we can say df over fe. So let me write here df over fe. That's going to be equal to 1 over 2, no? So it's 1 over 2. Well, we don't really need df over fe. Well, actually, we need df over de. But from here, we can easily see that df over de is actually equal to 1 over 3, no? All right, so no bad. Let's say this is 1 over 3. So that means that z is actually equal to 3x, no? All right, so it looks to me like we are making some progress here. Well, what else is going on? Well, how about we actually construct the height from C? Oh, there you go. Let's construct the height from C onto AB. So let's call this T right here. Can we actually figure out something relating Z and T? Because now we actually have this little triangle being similar with the bigger triangle constructed here. So writing the similarity ratio, Z over T is actually equal to, again, Z over T. That's actually equal to AE over AC, no? So AE over AC, or 2 over 6, or 1 over 3, no? So, okay, very interesting as to how we can make progress with these heights on here. So that means that T is actually equal to 3Z, no? Okay, very nice. So on one hand, we've got this relationship. Let's call it this relationship number 1. Let me copy this other relationship. T is equal to 3Z. So this would be relationship number 2. Well, now it looks like we actually approached Y, no? In the sense that now, well, see, we've got this triangle here is similar to this triangle here, no? So if you write the similarity ratio, Y over T, that is equal to BT over BC, no? So BT over BC. Well, how do we know BT over BC? Well, we don't know it yet, but we do have AT, no? AT is angle bisector in triangle ABC. So if we write the bisector theorem, BT over TC is equal to AB over AC, no? Well, AB is 1 plus 3, so that's 4, over AC is actually 2 plus 4, so that's 6. So this is equal to 2 over 3, no? Okay, good. But actually, we do not want BT over TC. We want BT over BC. But we can easily get from here BT over BC is actually equal to 2 over 5. So now we know that BT over BC is 2 over 5. So now we can actually get T as being equal to 5y over 2, no? And this is our third relationship. So to me, this problem is actually quite interesting because look at what's happening here. So actually we have y in terms of t, right? So for example, here we said y is equal to 2 over 5t. Then we have t in terms of z, no? So this means that y is equal to 2 over 5 times 3z. And now we have z in terms of x. So this means that y is equal to 6 over 5 times 3x, no? So there you go. That means that x over y is actually equal to 5 over 18. A very, very nice proof. We figure out x over y, and this is equal to 5 over 18. So we were able to compute AF over AT in what I think it's a very, very elegant proof. As you can see, absolute basic ideas being used here. All right. So thank you very much and see you at our next class.